Let's now look at some conditional probabilities. And throughout this example number 3 right here, we will be looking in details the understanding of what a conditional probability is. But then before we get to really understand what a conditional probability is, let's look at answering question A right here. So reading the example itself, and this is before I put up any question. Now, so there are 10 markers in a box, and those are labeled with numerical labels from 1 to 10. Those markers labeled from 1 to 4 are in blue color, and those labeled from 5 to 10 are red. And so if we randomly select one marker from the box, let's find the probability of, question A here is nothing new. Find the probability of about getting a blue even. And so to understand the problem even further, here, once we randomly select one marker from the box, the question here wants to find the probability, so P in parentheses. So blue even really means, and we have seen that throughout our example 2, then blue even means we're looking for, on one hand, being a blue marker, and on the other hand, so this is actually an AND keyword here, even though it was not specifically written, but I'm looking for blue and being an even number. So even or odd is a property that belongs to the numerical labels, and being a blue or red, those are the different properties that belong to the color of your marker. And so now, in order to find that answer, let me quickly bring up a quick picture of your sample space. It's actually quite simple to draw the sample space here. We don't really have to draw all the markers, but the markers have two important characteristics. It has, each one of the marker has color, and it has numerical labels. So the description of those markers saying labels from 1 to 4 are in blue colors. I'm going to go ahead and just draw 1, 2, 3, 4. Those are just fine to represent the blue markers, label getting the numerical label from 1 to 4. And then the other markers are from 5 to 6 being red colors. So 5, 6, 7, I meant from 5 to 10. So 5, 6, 7, 8, 9, and 10. So these are simply representing the different markers, getting different labels like that. And so now, answering our questions that we were looking at earlier, then looking for the probability of having a blue and even, being blue and even. So the only count that meets two requirements at the same time here are these two counts here, being blue and being even. And so back to the answer, the question itself. The answer now is simply 2 out of, and we have a total sample space containing 10 outcomes. So 2 out of 10, that gives me, as a reduced fraction, 1/5. And so we found our answer here. And so this question was brought up after we got it solved here. We're starting to wonder, it has nothing special. Why do we really have to worry? And we don't see anything explaining about a new concept of a probability. So the next question I'm bringing up here is find the probability of getting a blue marker. So still, we're randomly selecting a marker from that box, but now we want to find the probability of getting a blue marker, given that it's the marker that you're picking up, given that it's it is an even number. So the intention here is that the even number here is the numerical label on the marker itself right here. And so once again, the question here is stating as find the probability of getting a blue marker given that it's an even number. And so there are a lot going on in here in this question. Now, first I need to make it clear that this question has the exact two simple events being involved, being blue and being an even. However, this is strictly not looking for blue and even. It's a different story right here. Notice that we have a keyword given that here. So if this question is exactly the same way as how you find blue and even, then we don't even have to worry about wording it in such a lengthy way like this. And so there is a whole reason for why we put that word given that. It's an even number here. And so first, let's learn to set up the symbolic expression for this kind of problem right here. So in the end, the entire statement I'm writing here, I want to get a blue marker given that it's an even number. And your question is famously a probability question. So we are still going to prepare for ourselves a capital letter P with an empty parentheses. The two events being involved here are still exactly those two same events we worked with in the earlier question. But this time the keyword given that here, we're going to be using a vertical line here for that term given that. So given that in probability term, it has a symbolic statement, a symbolic expression that using a vertical bar like this. And this means given that. That's a symbolic substitution for given that. Yeah. And so the whole statement reads, I'm looking for the blue marker. So I'll put blue before that vertical bar, and given that being an even number, so I'm going to put even the other requirements behind the bar right here. And so here I'm going to just strictly stick with that order. Right now, the way how the problem was worded, blue as one requirement comes before the term, the logical keyword given that, and then even is the other requirement that comes after the phrase given that. So strictly in that order, then blue, then the bar to separate the two, and then there's even. So let's really try to understand what given that is indicating for us. The term given that here in probability, it means we are going to look for, the intention here is that truly we are looking for, we look for blue. That's our main purpose. We're looking for blue. But then we're looking for blue not in the entire box. We're looking for blue within the even numbers. All right, so once again, I restate this. This statement, this symbolic statement is a symbolic expression of our question here, but given that this bar here, or worded way, we're saying that we're looking for blue given that it's an even number. But truly behind the scenes, and the real philosophy here, the real fundamental here, is that we're looking for blue, but within the even numbers. All right, so here we are, the 10 markers here, 2 different colors, 10 different labels. Now, remember the term that really caught my attention here, and I was reading that out clearly in capital letters, being within. So that actually means we have to turn our attention, we narrow our attention to find all the even numbers first, actually. Even though that's not what we're looking for, but we have to turn our focus, we turn our attention first to the even numbers. So these guys are the even numbers, regardless of what color they are. Just as long as you found some even numbers, those are what matters for us. And then once you found these things, once you successfully restricted your attention to within these even ones, as written and indicated in the problem, then we're now looking, see, among or within these even ones. Where are the blues? The blues are here. So these are the blues. So really in that way, what I have now is there are 2 blues inside of 5 evens. See, these are the 5 evens. We turn our, remember first we turn our attention to only focus on the evens. Then within these 5, inside of these 5 even ones, we're looking for the blue. So now our answer is a 2/5. And that is the answer this question is looking for. 2/5. So indicating that there are 5 even numbers, but we're looking for the blues within those even numbers. So there are only 2 blues within the 5 even numbers. And so that is how we find a conditional probability. And here is another way to approach the exact same question. I'm looking for the probability of blue given that our marker is already an even number. And so looking back into the quick little illustration figure we brought up earlier, admittedly we already found the answer being 2/5. I'm putting it aside right now. That was our answer for the exact same question. But let's have a look one more time right here. You see how the 2 markers here, 2 and 4, gets double checked? So being double checked here really means there are 2 of them, but 2 out of 10. What is this ratio 2 out of 10 here is indicating? We have 2 markers that have, and remember double checked means the checks at the bottom here are those checks that meets the requirements for being an even number. So these are what the checks in my bottom line. The checks on top of the markers that I labeled there are indicating that these 2 markers also, remember I use the term also, so these 2 markers also qualify the other property of being a blue number. And so in other words, my ratio 2/10 right here truly is, and let me rewrite it in a proper fraction way right here, 2/10 truly is the probability for being blue and even. So that's what the 2 here is for. We got 2 markers, but that 2 in my numerator of the answer 2/5 we've had, really we can think of that as these 2 markers, they satisfy 2 requirements. They meet 2 requirements, being the even numbers, and also they are being the blue markers. And so in that way, if we're looking at that ratio out of the entire container, then we have a ratio 2/10. I'm not going to reduce this yet. And then we look further that the 5 checked here in the denominator, if we just simply looking at a separate probability, looking for simply the even number, then this is going to be 5 out of 10. Because in the entire container, if we only worry about being even number, then we got 5 labels, 5 markers that qualified the event being an even number. And so let's do a little bit of algebra here, but now if I put the 2 fraction, if I put the 2 ratio there, 2/10 as for the probability of blue and even, and if I put that on top of my other fraction 5/10, which came out from the probability of being an even number, then, or equivalently, we're looking at the probability of blue and even over probability of even, then canceling out the 2 fractions here, that gives us 2/10 times 10/2, 10/5 I mean, which will eventually cancels out and come back to being a 2/5. That gives us the answer here. So what did I try to say right here? I actually tried to point out that there is a formula existing behind the scenes here. The answer we're looking for from the beginning was the answer for probability of looking for blue, given it's an even. And the way we find that here through this alternative explanation is that the 2/5 ratio that we came to as the final answer here can be thought of as we're looking at the probability of being blue and even, and that was the whole reason why I brought up question A right here, for you to remind yourself that we can always find blue and evens, a compound event. And this thing here, a conditional probability, is even though not exactly the same, but they are related. So I'm going to find the probability of blue and evens as a 2 out of 10 and dividing that probability by the probability separately for being evens. And so putting that into our example here to formalize the step here, then after all that explanation, then I can see that blue, I can set up the formula as a probability of being blue and even, and divide that by the probability of being even. And then that also gives me the probability of being blue and evens is a 210 divided by the probability separately for looking for evens is a 5 out of 10. And that's similar to how I put the math earlier. 2 over 10 times 10 over 2, 10 over 5. And the 10s got cancelled out. And here we're looking at a 2/5 again. Same result. And so for conditional probability, again, there's a generalization that we have learned here through our example 3 right here. Question B. Let A, B, be 2 events. And really 2 events, but usually we just, at our level, we just use the simple events right here. And then the kind of conditional probability problems is being written like this. Symbolically, we're looking for the probability of the event A given that we are in the event B. And so one approach, we can just simply rely on that fundamental. So here we give the count. We give the count based on the fundamental that I explained about. Okay. We look for A, but within B. So one way to approach the problem, we can just simply count anytime that your sample space is available for you to search through, then we can just simply count, right? Based on this theme right here, we're looking for A, the probability of A, but within, meaning we turn our attention to within B right here. And then that's a theme that we can count successfully, and then we put that over the, and since we looking for A but within B means we turn the sample space to something smaller, not as big as the beginning sample space in a problem. And so that's one way how we can do it. Or we can approach the problem as a formula. And that's the reason why I gave 2 different explanations in the same problem here. But so probability of A given B can be found by, on one hand, we can find a separate probability for A and B. And then we're dividing that by the probability of A. Probability of B. The rule of thumb here to remember is that in case you keep forgetting about the formula, then we always divide by the probability of the events that stays behind the bar here. And so after we learn, hopefully clear enough about how you can find a conditional probability, then let's apply what we've just learned into answering another question. So what about finding the probability of, in question C here of our example, getting A, or how about I'm going to say getting an even number. Given that, so be aware that now we're about to work with another conditional probability. Given that it's a blue marker. And so there's that exact structure again. there's one event being mentioned, looking for even number, there's that famous phrase that we just now learned, given that. And then after that phrase, given that, we're actually looking for blue marker. And if you notice a little more closely, this question C is exactly the same. I mean, I shouldn't say exact, but this question C is actually still using the same two events, being an even number and being a blue number. The only difference is that we switch around their orders of these two events right around that phrase, given that, right there. So grammatically, that's what we recognized. And now let's set up the symbolic statements right here. So P, find the probability in parentheses. The vertical bar representing given that is here. And now, but this time being even, being blue, these two primary events, we're going to switch their order. So even stays before the bar, and being a blue marker stays behind the bar. So there's even and there's blue here. And so now, once again, let's approach in two different ways again. In one hand, let's approach through directly counting, because we do have the actual sample space being presented here. So let's count through and get yourself comfortable with that. All right, so here we go. This is our sample space right here. So we have those markers with labels 1, 2, 3, 4, and the red markers with labels from 5 to 10. So 5, 6, 7, 8, 9, and 10 again. And so now, this time our question is looking for, we want to find the probability of being an even, given that it's a blue. So remind yourself, in that way, we really are, our guidance here is to look for, the events behind the bar, the events before the bar is actually being an even number. So we're looking for even numbers. But within, and this term within once again is important. We need to narrow our attention within the blue ones. Right, so we look for evens within blue. So these are all the blue. So let's lay down our foundation first. Let's look for blues. So the blues are all here. There are 4 blues. And now within these, once you turn your attention to restrict your attention to all within these 4 blues right here. Now the even numbers are these 2. All right, and so now after all that explanation, let's get back and give our answer there. And so here, after looking through the sample space and do the proper counting, then the answer turns out only 2 out of 4, which reduces down to a 1/2. And so that is our final answer. And once again, as a different approach right here, probability of even, given blue, I can think of that as, let's find the probability of being even and blue. But notice, the probability of even and blue is also the same as the probability of being blue and evens. Now, in this compound statement, if we switch the order of the 2 events, that doesn't change our answer. But so now we actually seen in the earlier approach, I already found the answer to this, but we actually did have an answer different from part B, even though we still use the 2 same events. Because here I'm dividing by the probability of blue. So notice how I explained earlier when I was writing down the formula. If we are using the formula, then make sure we put the denominator being the probability of whoever the events behind the vertical bar. And so in that way, continuing with the work here, then this gives me, now this question here, probability of being even in blue, is nothing but just that answer we've had from question A right here, 2 out of 10. And that is being divided by, but being blue, there are 4 blues, but counting in through the whole sample space is a 4 out of 10. And so mathematically, it's the same as, we can continue our work here by being algebraically, it's a 2 tens times 10 over 4. And now once again, the common factor 10s here got cancelled, and here it becomes 2 over 4, which in turn again reduces down to 1/2. So I briefly mentioned this when we were still working on question C, when we were still working throughout the example 3. But now let's re-emphasize. If we now look at the answers from the two question B and C of example 3 just passed, then now we realize that probability of A given B is not always the same as the probability of B given A. So just because we switch around the order of the two probabilities of two events around the given that symbolic line right here, but that doesn't mean we just simply that doesn't mean they have the same answers. I sometimes see students of mine running into mistakes like this, and it becomes quite common sometimes that the probability of even given blue before any careful thinking. Some of my students in the past quarter just rushly take this 2 over 5, but put it in the denominator, so 1 over 2 over 5, and they get the kind of answer a 5 over 2. So you can double check for yourself if this kind of answer is correct or not. But so I think I saw the reason why some of my students in the past quarter were doing that mistakes. And by the way, if we notice the 2 over 5 that the person or some of my students in the past quarter made this mistakes, and you can kind of see where that 2/5 came out from. They came out because this is the probability of blue given even. So once again, for those who made that mistakes, now I can guarantee you that we should never go that route right here. This is a huge error. The number one mistake is the kind of answer we have here is way above 1. 5/2 is greater than 1, and this is a huge violation in the work of probability. We can't have an answer that's greater than 1. And so also it brings another understanding here, not too important, but it's good that you can take that. But anytime you're working with probability, we will never flip a fraction. We will never take the reciprocal of a fraction. So never take the reciprocal of a probability. And now let's look at what it means by considering the negation of an event right here and find the probability of a negation of an event. And so let's find out what negation of an event is through working out example number 4 here. And so in example 4, if we are spending some time reading through it, it's actually the exact same description as in example 3, but we're going to bring up different kind of questions regarding. So once again, there are 10 markers in a box labeled from 1 to 10, and then markers labeled from 1 to 4 are blue, and those are labeled from 5 to 10 are red. Randomly selecting one marker from the box, find the probability of, and so how about question A right here? How about I want to find the probability of not getting a blue. What's the chance of not getting a blue when you search for a random marker from the box? And so symbolically, looks like the way how it is here is we have the primary event being a blue. So we are looking for blue. That's the primary event right here. But then really, even though nailing down the primary events, and I shouldn't say earlier about looking for blue, we're not looking for blue. We're looking for not blue actually. But we identified that blue is our primary event. So here we're actually looking for anywhere but blue, anywhere not blue. And so putting a negation in front of an event here is what we refer to as negation. So this is a negation of an event. And that's what it means right there. So once again, we can easily, in a problem like this, we can easily count through, since our marker box, again, I have 4 markers, 1, 2, 3, 4, and I wrote 4, 3. But 1, 2, 3, 4, these are the blue markers, and I have the red markers going from 5 to 10. 5, 6, 7, 8, 9, 10. There are 10 markers altogether, and 4 of them being blue. So not blue simply indicate all I need to focus on is those 6 of those are not blue. So not blue, direct count here once you see your sample space, and it's just simply 6 out of 10. That reduces down to a 3 out of 5, which is good enough. And then here's another way to argue, but 6 or 10 markers altogether, looking for not blue. So another way to argue is that think about if you want to be outside of the blues right here. So outside of the blues means we're going to exclude the blues out. And so excluding means we are subtracting out. So what are we subtracting? We are subtracting the blues. So we're subtracting. So here's my subtraction sign. We're subtracting the blues. We're subtracting the blue, so take away the probability of the blue. But take away from what? Take away from 1. Take away from the whole data set, the whole 100% of your whole sample space. So 1 represents 100% or all that probability. So take all the blues out of the whole, and that once again mathematically 1 minus. We know that there are 4 blues out of 10. And so, and of course, finding blue, the probability of blue is, once again, we have to rely on the count right here. So 4 out of 10 being subtracted from 1, here, our answer is once again back to 6 over 10 here, or reduces down to a 3/5. And so that's a different way of arguing it. So my intention is to explain that sometimes when you have any event right here, and you recognize some events to be a primary event, and your question is looking for the probability in the form of not E. Then once again, one way you can do that by counting. We find that answer by counting. We can answer this by counting, or we can answer this by using a formula. Probability of not E will equals to, first identify the probability of E if it's easier, then subtract that probability from 1. And so in our class here, it doesn't happen too many times where we have to use so much formulas. However, these formulas I'm introducing here, there are people who are formally studying probabilities. Surprisingly, these formulas are extremely useful. But this formula here, among the probability experts, they refer to that as the rule of exclusion. So, in the same example, let's look for the probability of not getting a prime number. So here's another practice. Once again, remind yourself that we had a box of 10 markers labeled from 1 to 10, and 1 to 4 are being in blue colors, and 5 to 10 are being in red colors. And so symbolically, the question here can be represented as, so prime number is an event here, the primary event that exists among the numeric values. So we're looking for prime, but then we're negating it. So here is another perfect example for a negation of an event like that. And so looking for not prime, so let's approach that by, once again, two different approaches. So we can see that we have the 10 markers here. Allow me to write at the denominator at the bottom of the board here. 1, 2, 3, 4, 5. And then from 5 to 6 are the red markers. 5, 6, 7, 8, 9, 10. Alright. And so prime numbers are known to be those numbers being divisible by 1 or itself, but the prime number has to also be greater than 1. So these are the prime numbers. So to focus yourself to that. These are the prime numbers. So we got 5 prime numbers here in the whole sample space, but here we're actually looking for not prime. And so approaching the problem here by counting, then we're looking at, this is a non-prime, this is a non-prime, so these are the non-primes here. So we got the other 5. So the other 5 out of 10 here, since we have 5 primes, so non-primes within these given numbers, there's the other 5. So reducing that down to a 1/2 as our final answer. And same problem, if we are approaching that using the exclusion, the rule of exclusion that we've learned, then the probability of not prime can be found by simply nailing down the probability of the primary event being a prime, and then we subtract that probability from 1. And so once again, I purposely do 2 different approaches here so everybody can be comfortable with 2 different styles. But probability of prime here, once again, in my count, there are 5 primes out of 10. So 5 primes out of 10. And we're subtracting that, we excluding these 5 primes out of the whole sample space. And so that's 1 minus 5 out of 10. And that, once again, doing the math, we're looking at another 5 out of 10, which reduces down to 1/2.